Have you ever wondered how something like a massive radar system on a ship sends out a super powerful beam of energy without, melting all the wiring? Well, I can tell you, it's not using a normal wire. That's where we're headed today, into the world of waveguides. These are the special pipes that make all kinds of high-frequency tech possible. So let's dive in.
So what's the big deal, right? I mean, we use wires for absolutely everything, from charging our phones to lighting up our entire house. So why the switch to these big, bulky metal tubes when we're talking about microwaves? It's a fantastic question. And the answer really gets to the core of how this high-frequency energy acts. It's a little weird.
Okay, so this picture really says it all. On the left, you've got a regular two-wire line. At really high frequencies, it basically becomes a leaky hose, just spraying that precious energy out into space. Super inefficient. But the waveguide on the right, it's like a perfectly sealed, high-tech pipe. It keeps all that energy locked inside, making sure it gets exactly where it needs to go.
Here's our game plan for this explainer. First, we're going to break down the problem. Then, we'll define the solution, the waveguide itself. After that, we'll get into the physics of how the energy actually travels, cover the rules of the road that govern it, and wrap up with the practical bits and pieces you'll see in a real system.
All right, so let's start with the problem we're trying to solve. It all boils down to the strange and wonderful world of microwave frequencies. We're talking about this huge chunk of the electromagnetic spectrum where the normal rules of electricity kind of start to fall apart. And here is the absolute key takeaway. The higher the frequency, the shorter the wavelength. I want you to think of it like this. A low-frequency wave is like a long, slow, lazy ripple in a pond. But a high-frequency microwave is like a really short, fast, energetic chop. And that choppy energy just loves to leap off a wire and radiate away, which is great if you're an antenna, but it's terrible if you're just trying to get power from point A to point B.
So if energy is desperate to escape, what do? Simple. We build a better box for it. And that is exactly what a waveguide is. It's basically a high-tech pipe, custom designed to carry that jumpy, high-frequency energy. Now here is your official, exam-ready definition. The two words to burn into your brain are hollow and conductive. Notice there's no wire running down the middle like you'd find in a coax cable. The energy actually travels through the empty space inside, and those conductive metal walls act like mirrors, keeping it all contained.
And this isn't a one-size-fits-all kind of deal. Not at all. Waveguides come in all sorts of shapes. You'll see rectangular ones most often, but also circular and even elliptical. And those shapes, and more importantly, their exact sizes, are super critical. They are precisely engineered to control exactly which frequencies are allowed to pass through.
So, you might be wondering, if these things are so great, why don't we use them for everything? And the answer is a classic engineering trade-off. On the one hand, they are incredibly efficient, way less energy loss, and they can handle a ton of power. But on the other hand, they are big, they can be heavy, and they're expensive to make and install, especially for lower frequencies. That's why your toaster's never going to be powered by a waveguide.
Okay, so we've established that a waveguide is a hollow pipe, but how in the world does the energy actually move through it? This is where we have to shift our thinking away from electrons flowing in a wire and start thinking about invisible fields moving through space.
First up is the electric field, or just the E field. The absolute easiest way to picture this is to think about a capacitor. You've got two metal plates with a voltage difference between them. The E field is that invisible field of force, that stress in the space between the plates. It's the push or the force part of the wave.
And visually, it kind of looks like this. We draw these lines of force, and they always start on a positive potential and end on a negative one. So inside a rectangular waveguide, they'll stretch from the top wall to the bottom wall. And see how some lines are closer together? That just means the field is stronger right there.
Now, an E field never travels alone. It always has a partner, the magnetic field, or H field. This is the motion part of the wave, and it's created by the movement of electric charges or current. Just think of the magnetic field that pops into existence around a coil of wire the moment you run current through it. Same idea.
And here is the key difference between the two. Unlike E fields that start and stop, H field lines have to. They must form complete, closed loops. They don't have a beginning or an end. Inside the waveguide, these swirling loops of magnetic force travel along with the E field.
So how do these two fields work together to actually move energy? It's all about right angles. It's this beautiful three-dimensional dance where the E field and the H field are always perpendicular to each other, and they're both perpendicular to the direction the energy is actually traveling down the guide. It's this interaction that literally pushes the energy forward.
Now here's where it gets really cool.
the energy doesn't just shoot down the pipe in a straight line. Nope, it actually bounces off the walls in a zigzag pattern. Seriously, think of a billiard ball ricocheting off the rails of the table. Because it's taking this longer zigzag path, its actual forward speed down the guide, we call that group velocity, is just a little bit slower than the speed of light.
Okay, so this zigzagging isn't just random chaos. It's actually governed by a really strict set of rules. And those rules are set by the physical size and shape of the waveguide itself. It's time to talk about the rules of the road.
The most important rule, the one you absolutely have to know for any test, is the cutoff frequency. Every single waveguide has a minimum frequency that it can handle. If you try to shove a signal in there that's below this cutoff frequency, it just gets rejected. It won't go through. And this frequency is determined almost entirely by the waveguide's widest dimension, what we usually call the A dimension.
So why does this matter? Well, you can think of the waveguide as a high-pass filter. It only lets frequencies above a certain point pass through. If the wave is physically too big for the pipe, meaning its wavelength is too long to fit properly inside, it just can't propagate. It gets blocked at the door.
Now, the specific pattern that the E fields and H fields form as they dance down the waveguide is called a mode. There are lots of different patterns possible, lots of different modes. But in the real world, systems are almost always designed to use the simplest, most efficient one. And that one has a name, the dominant mode.
All right, enough theory for a minute. Let's get practical. How do we actually use these things? How do you get energy into one of these pipes, and how do you get it out at the other end? Let's take a look at the Waveguide toolkit.
It really boils down to three main methods. First, you can use a probe. This is basically a tiny little antenna that you stick inside the waveguide, and it talks to the E field. Second, you can use a loop of wire, which creates a little magnetic field to interact with the H field. Or third, you can just cut a carefully shaped slot in the wall of the waveguide, which lets the energy radiate out. That's actually how a lot of radar antennas work.
Okay, deep breath. Let's do a super fast recap for your study notes. A waveguide is a hollow pipe for microwaves. The E field is the voltage part of the wave. The H field is the current part. Cutoff frequency is the minimum frequency that's allowed, and it's set by the waveguide's size. A mode is just the pattern the fields make inside. And group velocity is the actual forward speed of the energy as it zigzags along. Got it?
All right, quiz time. Let's see if you can answer these questions. If you can, you've got a fantastic grasp of waveguide basics. What's the biggest limitation at lower frequencies? What makes the energy travel? What do we call its forward speed? What are the two main mode categories? And finally, what are the three ways to get energy in or out? If you got those, you're in great shape. Thanks so much for joining me, and happy studying.